Imagine this. Your AI agent permanently deletes a user's critical data instead of just updating it. And the worst part, you literally have no way to stop it before the damage is done. Talk about a nightmare scenario. Welcome to the hidden layer, decoding artificial intelligence. Today, we're tackling that terrifying reality head on. We're going to break down exactly how to build a safety net for your models, and more importantly, how you can actually apply this breakthrough research in the real world today. Look, if you're building multi-agent systems, you know this problem all too well. What actually happens when your AI makes a bad call to a live API? Well, today we are decoding a breakthrough architecture called inference time feedback. It's designed to catch AI hallucinations and logic errors before they ever hit your APIs. And hey, stick around, because later in this explainer, I'm going to let you in on a secret technique these researchers use to automate and optimize this exact system so it actually gets smarter on its own. All right, let's dive into Section 1, the AI tool calling crisis. When we let large language models interact with external APIs, they face some pretty massive challenges in selecting the right tool and getting the arguments exactly right. And honestly, right now, we rely way too heavily on post hoc evaluations to recover from these errors. Basically, the AI makes a mistake, executes it, realizes it messed up, and then frantically tries to fix it. But in the real world, once an AI permanently deletes a user's alarm instead of updating it, or, sends a completely broken API request that racks up your server bill, the damage is done. Trying to recover after the fact is just incredibly complex and expensive. We desperately need proactive evaluation. Which brings us to Section 2, Meet the Reviewer Agent. The solution researchers came up with here is surprisingly elegant, and it's something applied engineers can start implementing right away. It's a dual agent architecture that completely separates execution from review. So instead of letting the main AI directly access the tool, they use a progressive feedback loop. First, a primary agent generates a provisional tool call. Think of it as a rough draft. Then a secondary reviewer agent steps in to evaluate that draft. If it spots an error, it forces the main agent to revise it. The actual tool execution only happens once the reviewer gives it the green light. It's basically acting at an intelligent firewall. Let's see what this looks like in practice. Say a user asks for the weather in New York City. The primary tool calling agent drafts a call, but it tries to use Celsius, and it uses the abbreviation NYC. Well, the proactive reviewer agent instantly catches that formatting error before execution. It points out, hey, US cities should default to Fahrenheit, and we need the full city name here. So it sends that feedback right back. The base agent takes the note, corrects the format to Fahrenheit, changes the city to New York City, and drafts a brand new call. The reviewer double-checks this revised version, gives it the thumbs up, and only then does the tool actually execute. The error was entirely caught in the hidden layer long before it ever triggered the live weather API. Moving right along to Section 3, Helpfulness versus Harmfulness Metrics. Now we have to be honest here. Adding a secondary proofreader introduces a brand new risk. What if the reviewer is just overly skeptical and ends up breaking a tool call that was actually correct in the first place? To quantify this exact trade-off, the researchers introduced two metrics: helpfulness and harmfulness. Helpfulness measures the percentage of base agent errors that the feedback successfully corrects. Harmfulness, on the other hand, measures perfectly correct responses that the reviewer incorrectly degrades or breaks. Obviously, we are looking for a net positive value here. And this is where model selection becomes absolutely crucial for that reviewer role. You don't just want any standard model double-checking your work. When comparing standard models against reasoning models, the performance of O3 Mini really stands out. This reasoning model dramatically outperformed the standard models in maintaining that super delicate balance between catching real errors and leaving perfectly good code alone. To put that into perspective, by using a reasoning model like O3 Mini as the reviewer, engineers achieved a massive 3.1 to 1 benefit to risk ratio, meaning the reviewer fixes over 3 times as many errors as it inadvertently causes. That is a massive net gain for your system stability. Let's move to Section 4, Real-World Latency and Deployment. Now, if you are an applied engineer listening to this, you are probably screaming, but what about speed? And that's a fair question. For simple, single-turn tasks, like just asking for the weather, adding a reviewer introduces a pretty heavy 6.2x latency penalty. But contrast that with complex, multi-turn, stateful agents, where the AI is performing long episodes of work. Over those longer tasks, that cost is amortized across many turns, dropping the overhead down to just a 2.4x increase. This data arms engineers with a highly strategic choice. If you have a high-volume, real-time app, you might want to stick to selective feedback. But for multi-turn workflows, a 2.4x overhead is incredibly viable. You're basically trading a little bit of speed for bulletproof reliability in high-stakes ATI workflows where bad executions cost serious money, or even worse, ruin user trust entirely.
Okay, Section 5, bonus, automated prompt optimization.
All right, here is that secret technique I promised you at the very beginning to make your reviewer bots smarter without doing endless manual prompt tweaking. They used a framework called GPA. That stands for Genetic Pareto Prompt Evolution. With this, the system automatically observes where the reviewer failed and actually optimizes its own prompts. By allowing the model to refine its own rules, the irrelevancy detection score boosted by an impressive 2.8% without any manual intervention. The prompts just got longer, more detailed, and far more accurate, entirely on their own. Let's wrap things up with Section 6, Building Verifiable AI Agents. Let's bring this all together so you can start applying this architecture in your own production environments today. The absolute beauty of this approach is that it requires literally zero retraining of your existing base models. If you're using something like the Agent framework to build your agentic pipelines, implementation is incredibly straightforward. You just define a new verification step in your Agent routing, drop in a modular reasoning reviewer like O3 Mini, and set it to proactively intercept tool calls before they hit the execution layer. You get to control the trade-offs and prevent downstream API disasters without overhauling your entire existing architecture. It's a total game changer.
So it leaves us with this really fascinating thought. As we shift from post-hoc recovery to this kind of proactive inference time evaluation, just how reliable can our multi-agent systems truly become? Think about your own projects for a second. If your AI had an internal reviewer catching every single hallucinated API call, what catastrophic errors could you eliminate before they ever see the light of day? Thanks for joining me on this explainer. Until next time, keep building smarter.